Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 352 Nuclear Physics 1. Today, I will be covering the 11th lecture of this course, and that is the continuation of the previous lecture, the Semi-Empirical Mass Formula. Today we will be talking about the quantum corrections to the semi-empirical mass formula. First, I will give the learning objectives. At the end of this presentation, the student will know the quantum corrections to the semi-empirical mass formula, and those quantum corrections are known as the asymmetry and pairing term. As we have seen in the previous lecture, that with this semi-empirical mass formula, the student will be able to explain the binding energy per nucleon curve of the known elements. In this course, we are following the book Introductory Nuclear Physics by Kenneth S. Crane, 3rd edition. In this lecture, some of the figures are taken from this book. We will start with the form of this binding energy based on the semi-empirical mass formula, and in this expression all the terms are there. The first one is the volume term, the surface term, the Coulombic energy, the asymmetric term, and the pairing term. So in this lecture today we'll be talking about the asymmetry term and also the pairing term. The asymmetry term is negative. We will see the reason for the negative and the positive term. This pairing term can be negative and positive depending upon the configuration. In my previous lecture, lecture number 10, I have explained these three terms, and also in that lecture I have explained the background of this formula. So before proceed, I will recommend to first look this lecture number 10, and then you will be able to understand the quantum corrections. So with this binding energy expression, as I told you, one can describe the binding energy per nucleon curve against a curve. So we will start with the pairing term, as we have done previously the three terms. So today we will be talking about the fourth term, the asymmetry term. Now this asymmetry energy is proportional to the neutron and proton number difference. That is, it is proportional to the n minus z, that is the difference of the neutron and proton number. Now this difference is the same as 1 minus a minus 2z. Since we know that a is the nucleon number is equal to the sum of the neutron and proton, so from here one can change this n to a minus z, and then this will be a minus z, and they can be conveniently write in this form, that is 1 minus 2z. So this 1 minus 2z in the asymmetry term is nothing but the difference of the nucleon number, that is the neutron minus the proton number. You will see in the coming lecture, once we describe or analyze the various applications of the semi-empirical mass formula, that is this form will be convenient in writing this formula. Instead of n minus z, we have a minus 2z. Now, as I told you that this asymmetry in the neutron proton number. So if this neutron and the proton number are equal such that this A will be Z by 2. So if there is a symmetry in the neutron proton number, so the system will be symmetric. And if the neutron number is greater than the proton number, so that there will be an asymmetry in the number. So the first thing that we need to look whether these two cases are observed in all these elements and also some of the isotopes or not. So with this, the first case, which is the n is equal to z trend, that is pretty much the case with the lighter nuclei. So as I have told you in my previous lecture that we can divide uh, these elements in different groups. For example, this will be the lighter weight elements, then we have the intermediate and the heavy weight elements depending upon the nuclear number. So this n is equal to z is a trend of these elements which are lighter. We will see this, but once this neutron number is greater than the proton number, the second case, that is the case with these intermediate weight element or the heavy weight element. That is, once the A number is large, so that means the A greater means there are large number of protons. So to overcome the Coulombic repulsion between the proton inside the nucleus, so the stability of the nucleuses, the stability of all the system requires even greater number of neutron to hold the nucleus together, so that there will be strong nuclear force exist as compared to the Coulombic repulsion. So for intermediate and heavyweight element, this trend is pretty much there, and this n is equal to z is the trend which usually followed by the lighter elements. Now, before we come to this binding energy curve, this binding energy expression with respect to the asymmetry energy, we can describe these elements and also some of the isotopes of these elements in terms of neutron and proton number. So, so if I'm talking about in this region, that is small number of neutron, on this axis we have the neutron number, and on the y-axis we have the proton number. So this region will be similar to these elements. And once I'm talking about this portion, that is the neutron number is this much and the proton number is this much, so that these are the, we can say that the intermediate weight elements. And also for neutron number greater than 100 or greater than 90, and on this side the proton number, so these regions will be the heavyweight elements. So we will see whether these trends are there with respect to the stability of the nucleus. So we'll start with this dark pattern. That dark pattern represent the stable element and also some of the isotopes, the stable isotopes of the elements. Now, this stability line, if we see here, is following the n is equal to z line, once we are talking about the lightweight elements, like these elements, as I told you. Now, but then this pattern deviates from the n is equal to z number. That is, beyond this point, all the stable elements have more neutron than proton. As I have explained that due to the Coulombic repulsion, the stability requires more neutron. Since this dark pattern lies below this n is equal to z line, that means all these elements beyond this, let's say up to this point, the neutron number and the proton number are equal because it is along this line. But once the A number or the nucleon numbers are more, then the proton number and neutron number, there should be an asymmetry to get the stability. So the first thing that we have discussed, that this pattern shows the stable element. This light gray portion, which lies again below this n is equal to z curve, these are also the representation of various unstable or radioactive isotopes. So they will convert some protons to neutrons in order to come to this stable curve. And similarly, below this dark pattern, these elements below this gray portion, then here some of the neutron will convert to proton in order to get stability. So this conversion is pretty much the case. So this asymmetry in the neutron proton number exists, and because of this asymmetry we have a term in the binding energy. So one can see that there is no such case in which the proton number is greater than the neutron number. That will be the case if we have some sort of elements over here, right? So because nuclear force holds the nucleus together, so the more proton means more Coulombic force, and that's the reason that is all the stable elements lies below n is equal to z, and even these isotopes requires to convert some of the protons to get to the stable line. So now after looking at this the usually known as the NZ plot, we are now in a position that is in order to get stability, the nucleus undergo that conversion. So as an example, we have two systems. Let's say A is equal to 16, that is the mass number is equal to 16, and we have one system in which the proton number and the neutron number are equal. That is the n minus z, as I have explained here, that is equal to 0. That is the case where A is z by 2. Here it is important that this is not just a representation of these lighter elements. This is just a random number. You can take any number, but just to explain this with the help of this cartoon, we have taken this A is equal to 16. It doesn't mean that this is valid only for the lighter elements. So now, as I have explained this NZ curve, that is for a system to get a stable configuration and to overcome the Coulombic repulsion. For example, this nucleus needs to convert some of the proton to neutrons. so that to have a stable configuration like this. As I have explained, that this conversion is pretty much the case with the within the nucleus. So in order to get the stability, let's say two uh, two protons are converted to neutron. So that, let's say, in this, due to this conversion, uh, uh, it comes to this dark pattern, this stable pattern. So now the situation is that due to that conversion, those converted protons cannot lie uh, in the same energy level. It will occupy the free uh, available energy levels, or the higher states energy. Now, when this proton, the previous protons, and now it converts to neutron. So due to this conversion of the proton, and as a result, those two protons are now going to the neutron pool and acquiring higher energy state. So due to this conversion, the overall the system energy increases. So once the system energy increases, that means the binding energy will decrease. So this is the negative sign here. So if these electrons are here, that is a configured state, the lower energy, lowest energy state, let's say, and then due to conversion, the two particles now will acquire the higher energy state. So due to this conversion, the neutron proton energy asymmetry exists, and due to that asymmetry, now the overall system energy will increase, and that will decrease the binding energy. Now, before I comment on the overall expression of this asymmetric term, let's discuss this 1 over A dependence. This A, remember, is the n minus z. 1 minus A minus 2z represent n minus z. And now this binding energy varies as 1 over A. So this behavior is because the fact that the size as the the nucleon number is increasing, that is, uh, elements with more nucleons, that is, since we are going towards this portion or this portion or over here, so the spacing of the energy level, let's say we have one level, two level, one dimensional figure, three level, four level, and then if there are more number of nucleons, so that they will occupy, so though the spacing of the energy level shrink, or in another word, the spacing between the level decreases, uh, as the case with the atomic shell. So then, with all those closely packed shells, now it doesn't matter whether the proton are lying here or very uh, closely packed shell, and it transferred to the shell, but because of the large size uh, of the system, that is with large A, the energy difference is not that much. That is, those uh, previously protons, which converted now to neutrons, their energy difference is not that much, as we know from the atomic shells. That is, that is, once the system is having large number of nucleons in this case, so the shell energy differences are not that much. So that's why once we are talking about a large system here or here, so the binding energy will automatically decrease, because because uh, decrease with respect to that asymmetry in number. Remember. Now, the actual form of this asymmetric term can be derived once we are in a position mm, mm, to have those nuclear shell models that we will do in the later part of this course. And in the shell model, this asymmetry energy can be derived by modeling the nucleus as a Fermi wall of protons and neutrons. And just to comment on this, the first term, while deriving based on those Fermi model, the first term contributes to the volume energy, and the second term, which is the square term, the A minus 2Z, and due to the asymmetry term, which will be of this form. So we have explained the various aspects, but the complete derivation, how this form comes, that we will done after the shell model. So after this, now we'll be describing the last term, which is the pairing term. Now this pairing term is having this sigma, and that sigma can have value plus AP. This AP represent the constant, and due to the pairing term, pairing constant, and again there is a but with negative sign, and then a to the power minus 3 over 4. Now this is based on the configurations of the nuclei. That is, generally, experimentally, it is verified that even nuclei are more stable. So see, this will be having with plus sign. So this term will be added to the binding energy once we have a nuclei having even number of proton and even number of neutron, as compared to a system having odd A. Odd A nuclei means either the proton number are odd or the neutron number are odd. So in that situation, just as a reference line, then this sigma will be equal to 0. And another case in which a system having odd number of let's say proton and odd number of neutron, so those systems are less bounded, or they are not as stable as the even nuclei. So in that case, the binding energy will be somehow reduced by this amount. We will see the various magnitudes of these various terms on the coming slide. So that will reduce by this amount. So this pairing energy, which accounts for the tendency of the protons and neutrons pairs to occur, as even number of particle is more stable than the odd number, and that arises because of the spin coupling. Now this term, as I have explained, that this is because of the system configuration, that is, system having even, odd or odd A configuration. So that will lead to the different level of stability with respect to the binding energy. So we can we find the evidence for this pairing force simply by looking at the stable configuration or the stable nuclei found in nature. As an example, there are 4 nuclei with odd N and Z, but there are 1, 6, 5 with even configuration. So that is, the stability is linked with the overall the neutron proton number. So that is just to show by as an evidence that we have very small number of elements which are stable having this odd configuration, but we have large number of system having this even configuration. Now this is the complete form now, in which we have explained the volume term, the surface, the Coulombic, the asymmetry in the proton neutron number, and also the even odd or odd even configurations. So as I have explained this thing in my last lecture, that this is the contribution of only volume term which sets the overall trend of the binding energy per nucleon curve against the mass number A. Adding surface energy will shrink that towards the observational data, and also adding Coulombic force. Remember, we have discussed the the contribution of these different forces across different system. For example, lightweight elements, the intermediate and heavyweight. If you remember that the surface contribution uh, is more in the lighter elements than with the heavier elements. And today we have explained the asymmetry, and the pairing is not shown in your book, but this will make the curve, the binding energy per nucleon curve, around 8 MeV. That is, it will be close to the observational data by adding all these terms. So with this binding energy formula, which is based on empirical formalism, and partially it is inspired from the liquid rock model. So one can write, since this is a semi-empirical mass formula, generally this form usually known as the semi-empirical binding energy formula. So from here one can find out the mass formula. If you remember in my previous lecture, I have explained this m times c square is the mass energy of any nuclei. That can be equal to the z times the hydrogen, and then c square, and there will be c square, and then we have binding energy. So if we write just the mass, so that c square will be divided across the equation, so that there will be no c square, no c square, no c square, and here you have that c square in the denominator. So if we put this binding energy over here, and then one can find out the masses of various elements based on the empirical formalism. Now these constants must be adjusted to give the best agreement with the experimental curve, as we have discussed in my last lecture, that you can find different sets of value for these constants depending upon who is talking. Now a particular choice is given in your book, that is the AV equal to the volume constant is having 15.5 mega electron volt, the surface energy, the Coulombic energy. See the various contribution of this constant for which give this result. So these curves are based on these constants. Now based on these various energies arises from the volume, from the surface, from the Coulomb repulsion, from the asymmetry in the number, and also the various pairing configurations. We have just taken this from a nuclear physics book for 3 different systems. For example, this will be like, say, lightweight element, intermediate and heavy elements, in which we calculated the volume energy, that is this AV times A. So in the lightweight elements, the volume energy is this much. In the middleweight element, it is around 200, and then we have this in the heavyweight element. So large volume give rise to large energy. Similarly, the surface energies in all these 3 representatives of the lightweight, middleweight and heavyweight elements. So one can find out the magnitude, but if we see, these are fluctuating across these 3 regimes uh, of the mass numbers, but at the end the binding energy is around 8 MeV. So these calculations are based on this empirical formalism, and it comes out to be quite accurate in matching uh, the observational data. So this is just for the three regimes, that one is taken from here, the other one is here, and the third one is here. Now after this, now you can solve these problems, but remember, now you will be using the semi-empirical mass formula for these various elements to find out the binding energy per nucleon, and also the Coulomb energy. And the second problem, you need to find out the binding energy using the semi-empirical mass formula for this system. And you need to find out the difference between the actual value and the value that you calculate using semi-empirical mass formula. So with this, I need to thank you for your time.